Hello everyone and welcome to this new lecture. Today we'll be covering a new topic and a new tool which is known as the analytical hierarchy process, or AHP, which is one of the best or most important actually tools that comes under the umbrella of multi-criteria decision making. So basically in this lecture we will be defining what is AHP, and we will be learning about how to do a pairwise comparison, which is a very important step in the AHP process. Then we'll be learning how to rank the corresponding criteria and alternatives in an AHP framework, and last, choose the best alternatives that we have according to the corresponding criteria that we have used in our AHP analysis. So basically, by the end of this chapter, I hope you will be able to actually do AHP analysis and to use this tool to make better decisions whenever we're having criteria that we are basing our decisions upon. So the AHP is a multi-criteria decision-making approach proposed by Satie in 1970. It witnessed several refinements and improvements since then, and it's widely used to solve complicated decision-making problems. AHP can be seen as a general theory of measurement used to quantify events or decisions while incorporating subjective personal measures. So its important is that it can bridge the subjective, let's say, perspective of decision making to the objective needs. So in this regard, we're kind of transforming subjective, let's say, judgments. We're transforming those judgments into a more mathematical, let's say, framework and more sound, let's say, results. So accordingly, although the AHP method captures the subjective nature of decision making, it does not violate the mathematical soundness of the resulting choice. So this is very important. This is bridging the gap between, let's say, subjective decision making and more, let's say, mathematical or objective decision making. And this fact makes AHP suitable for establishing quantified measures in both the physical and also the social or psychological domains. So this is basically the, let's say, the importance of this method, that it does basically bridge subjective judgment to to actually more sound and mathematically based decisions. The AHP process in structure divides the problem into a hierarchical structure that includes the goal, the criteria, and the corresponding available alternatives. So the overall objective or the goal of the problem is positioned at the top of the hierarchy as our aim, and the decision alternatives and are placed at the bottom. And so we're having the goal at the top, the corresponding alternatives at the bottom, and in between we're having all the criteria and sub-criteria that can be used or is actually affecting our decisions for those alternatives. Okay, so using the hierarchical structure in AHP serves basically two purposes. First, it provides an overall view of the complex relationships inherent in the situation, and second, it helps the decision maker better assess whether the issues in each level are of the same order of magnitude, so he can compare such homogeneous elements accurately. So it's a visual tool at the same time, so it is appealing to use. It just let's say gives an overall view of the different criteria and alternatives and how they are affecting each other, and also it helps the decision maker let's say assess the issues in the same level or having the same magnitude. Okay, so as to provide or as to ensure homogeneity in the analysis. So this is actually a schematic, let's say, representation of the AHP structure. We're having at the top, we're having the corresponding goal. Then at the level 2 we're having criteria, and we might have also sub criteria below this, and finally we're having our alternatives that we are going to choose from. So This is our goal that we are aiming to reach. These are the criteria that are affecting our decisions, and these are the options that we need to select from according to those criteria in able to fulfill or to meet our final goal or objective. In this regard, AHP is a method that derives the ratio scales from paired comparison. So uh, paired comparison is whenever you're comparing relatively one criteria to another or one item to another. So the input to this comparison, to this paired comparison, can be obtained from actual measurements such as price, weight, if we're having like actual quantified measures, or from subjective opinions such as how much you prefer, let's say, apples to oranges. Okay, so it's just a way to give relative weights or relative judgment when comparing one item to another or one, let's say, criteria to another. So AHP allows some small inconsistency in judgment because humans are not always consistent, and this is actually I won't go to the mathematical background of this statement. However, just bear in mind that AHP allows for some sort of inconsistency in the judgment process. So it does accept some margin of minor inconsistency, and it is proven mathematically that this inconsistency does not violate the soundness of the judgment or the resulting decision. So just bear this as a statement and take it just in your background that we're dealing in this regard because we're having subjectivity sometimes. So if you say like I prefer, let's say, oranges to apples, or I moderately prefer them, so this kind of inconsistency in you saying that your judgment is acceptable in this AHP process. So the ratio scales, the corresponding ratio scales that would be actually calculated during this AHP process are derived from the principal eigenvectors, and the consistency index is derived from the principal eigenvalues. So we will see those in more details actually in the coming slides. So just an intro to the coming slides. So we're calculating the eigenvectors and corresponding eigenvalues of the corresponding matrices that we're going to build, and also will be actually let's say calculating our consistency index and consistency ratio that would prove the soundness or let's say the acceptance of the corresponding decision. Okay, so as for the corresponding, let's say, scale that we are going to use to make this paired comparison, we're having this scale from 1 to 9, 1, 3, 5, 7, and 9, which would reflect the intensity or importance of an absolute scale. So this is also proposed by Sati in the same theory. So if we say that two items are equally important, so the scale would be 1. If one item has moderate importance of one another, so it would give it a rank or a weight of 3. If we're having strong or essential importance, we're talking about 5. So if the number is 7, we can say that there is a very strong importance or preference for one item to another. And in the case of extreme importance, we would be using the number 9. So in this regard, we're having those main numbers in here and those intermediate numbers that we can use whenever we want to show intermediate values between two adjacent judgments. So again, back to, let's say, to number 1. What do we mean by equally important? We mean that the two activities or the two, let's say, criteria, let's say, would contribute equally to the objective. In the case of 3, we can say that experience and judgment slightly favor one activity to another. For the case of 5, we're having experience and judgment strongly favor one activity over another. And in the case of 7, we're having like more dominance demonstrated in practice, or this let's say the strongly favored situation is backed by let's say proof or actual practice experience. And in the case of 9, the evidence favoring one activity over another is of the highest possible order of affirmation. So we are highly sure and highly affirmed that this criteria is, let's say, more important than the other. So on the other hand, we will be having the reciprocals. Reciprocals are just the let's say if it is 3 for, let's say if A is 3 times let's say B, then B would be 1 over 3 of A. So this is the reciprocal value. So if activity P has one of these numbers assigned to it when compared with activity Q, then Q has the reciprocal value when compared with P. Okay. So this is, let's say, a scale. So for instance, if I slightly prefer apples to oranges, I would be using, let's say, this 3 towards the apple. However, if I, let's say, very strongly prefer oranges to apples, I would be using, let's say, number 7. So this is just a way how to use those kinds of scales to show preferences of one actual, let's say, item to another, or one criteria to another. So let's do an example together. Let's solve this example and show how we can build actually an AHP framework or structure and use it to calculate or to make our decision. So we're aiming to buy a car. This is our ultimate goal. This is our objective. We basically defined our criteria that would affect our choice. Basically, we're having 3 main criteria: the style, the cost, and the fuel economy. So these 3, let's say, factors are affecting our decisions or our judgment over the corresponding cars that we are looking at and the alternatives that we are choosing from. We're having the Honda Civic, the i10, the Ascot, and the Alto. So we're having basically 4 different kinds of cars or types of cars from different manufacturers that we are aiming to, let's say, select from or choose from based on the corresponding criteria that we have defined. So basically, we would be judging the Civic, let's say, for style, cost, and fuel economy, and then we would be judging i10 for those 3 criteria, the Ascot and the Alto, before we can make our let's say, judgment. So imagine, let's say, that we did this. So one person, the person who is going to do the corresponding decision, has done the pairwise comparison, and actually does consider the following issues. First, we are going actually to weigh or to rank the criteria. So although we're having those criteria, we need to know which criteria is more important for you than the other. So is style more important than the cost, or if the cost is more important than fuel economy, or fuel economy is more important than cost and style. So how these different criteria are weighing against each other is highly important in the AHP process, and we need actually to calculate this weight, and we use AHP also to do this weighing to differentiate or to prioritize the importance of each of these criteria. So imagine we have done this pairwise comparison, and this is how we do the pairwise. We build a matrix of 3 by 3. So we're having this kind of 3 by 3. We put the corresponding criteria that we are actually comparing. We put the style, cost, and fuel in the corresponding rows, and also the column style, cost, and fuel. And we would be actually using this scale to weigh the corresponding elements against each other. So for instance, the first in the diagonal, the style to style, cost to cost, and fuel to fuel, we will be having those ones. All right, guys, so because they are equally important, they are the same criteria. And now we start by actually comparing each criteria to the other. So in terms of the style, if compared to the fuel economy, we would say that the style is, let's say, slightly important than fuel economy for us, for the person doing the decision. However, the cost is, let's say, between equal and slight, let's say, importance to the style. So we're having this 2 in here, something in between, okay? So the cost would slightly or between equal and slightly affect our decisions more than the style. And if we compare the cost and the fuel economy, the cost is, let's say, important. This is the 4 here. It is between slight and slight strong importance over fuel economy in choosing the corresponding car. So this is how actually we did our comparison between the corresponding criteria. So now we're having those prime comparison. So we're having cost to style is 2, style to fuel is 3, and cost to fuel is equal to 4. So the empty cells that we are left are just reciprocal, guys. So if the cost to style is 2, then the style to cost would be 1 over 2. And if the style to fuel economy is 3, then this fuel economy to style would be 1 over 3, just the reciprocals. And we're having, let's say, if the cost to fuel is equal to 4, then fuel to cost would be equal to 1 over 4. So just for you to know, we first do the direct comparison, the preferences, and then we do the corresponding reciprocals, and we would be having this table that is actually showing the corresponding um, uh, comparison matrix based on these scales. Okay, so this is how we do our pairwise comparison, and now we're having this matrix that is showing the preferences among the criteria. So now that we have this matrix, we need to solve for the corresponding weights. And now there is a way. Actually, you can find several ways to do that. For the AHP, we'll be using one way in this lecture here. So we are going to actually let's say resolve this matrix in the following manner. So we first do calculate the sums for each column. So we're having here the sum of the style, the sum of the cost, and last the sum of the fuel economy. So the corresponding, let's say, scores that have been given, and then we would be using the corresponding sums to normalize our matrix. So I would be building a new matrix, which is the normalized matrix of this one. So I simply just divide each cell to the corresponding sum. So 1, I would be dividing it by 3.33, 2 over 3.33, and 1/3 over 3.33. Then 1/2 over 1.75, 1 over 1.75, and so on and so forth, to be building our normalized columns sum. Okay, so we're having this matrix as the normalized matrix based on the column sums. Okay, now that we have done that, we just do the corresponding averages of the corresponding rows. We do the averages of each row, and we get the corresponding weight for each criteria. So now, how can we read this? We read that the cost apparently is the most important, followed by the style, and then the fuel economy. So this comparison based on the actual preferences that we have done in the table, it leads us to this corresponding to these corresponding weights. So if we have chosen different, let's say, different preferences in the table, if another person is doing this, he or she maybe have chosen different numbers or different preferences, and therefore we would be reaching different weights. Just for now, this is actually the corresponding values. So we call this a priority vector. So, or even we call it an eigenvector that shows the priority of each criteria in our decision making process based on the preferences that we have put when we compared one criteria or other criteria with each other. Okay, so now we're having the first part of the hierarchy solved. So now we would know actually that the weight of the cost is 0.56, the weight of the style is 0.32, and the weight of fuel economy would be 0.12. And this is how they would sum up to a 1, and we call this the priority vector or the eigenvector of our corresponding let's say criteria solved. And now, and after we have calculated the actual weights of the corresponding criteria, we need to check for the consistency of our results. So the first step, we did the weights for the criteria, and the next step is to check or to prove the consistency of our corresponding results. And to do so, we need to calculate the consistency index CI and the consistency ratio CR. So in this context, AHP evaluations assume that the decision maker is rational, which means that if A is preferred to B and B is preferred to C, then A is preferred to C. So actually, I don't want to go with the mathematical actually background to this actually statement, but as a briefing, I can say that this consistency check would determine if the different preferences that are made by the decision maker are consistent with each other and does not contradict with each other. So we need to check for the consistency ratio to be less than 0.1 or 10%, and therefore if or otherwise that judgment would be untrustworthy, and then we cannot take those, let's say, judgments into consideration. So in this regard, and at the calculation level, to calculate the CI and the CR, we need first to calculate the lambda max, which is the eigenvalue, such as the A times X matrix A, which is the preference matrix made from the pairwise comparison, times the eigenvector X is equal to lambda max times X. And this is actually this is A that we have calculated first, and then this A matrix times eigenvector X should be equal to lambda max times the corresponding eigenvector X. So therefore, we need to calculate for lambda max. So to calculate lambda max, we need to resolve for these multiplication of matrices. So again, this is the initial matrix A times X, and this is lambda max, and this is again X. So basically, we multiply those two matrices, and you can review how to multiply matrices. Just the first row times the first column, and I would get our first, let's say, cell in here. So I would do this for you guys. So I multiply 1 times 0.32 plus 0.5 times 0.56 plus 3 times 0.12, and I would get this 0.96. And then for the second row, I do the same, 2 times 0.32 plus 1 times 0.56 and 4 times 0.12, and I would get the second one and the third value in the same process. So I would get this resulting multiplication, which is also equal to lambda max times X. And to resolve for lambda max, I would do the average of the divisions of those three values, 0.96 over 0.32, 1.68 over 0.56, and 0.366 over 0.12. So I would get the overall average to get lambda max equal to 3.02. Now that I have lambda max calculated, I can calculate the consistent index following this equation. I do subtract lambda max minus n over n minus 1, and n is the size or the dimension of the matrix, which is equal to the number of criteria that we have. So in this regard, we're having 3 criteria, and therefore n is equal to 3. Therefore, my consistent index CI would be 0.01. And to calculate the consistency ratio, I need to divide CI over RI, and RI is based on the size of the matrix. You can find those calculated online. So the randomness index for the matrix is based on the actual size of the matrix. So for the 1 and 2, we're having zeros, and for 3.58, for a matrix 4 by 4.9, so on and so forth. So I just divide my CI, which is 0.01, over RI, which is 0.58, to get 0.017, which is less than 0.1, meaning that my results are consistent and therefore my judgment is trustworthy. So we're having sufficient consistency to make our corresponding decision. So our third step, after we have actually ranked our criteria and also checked for the consistency of the results, the third thing we do is to rank our alternatives according to each of the corresponding criteria. So in our example, we're going to rank, let's say, those 4 alternatives: the Civic, the i20, the Ascot, and the Alto, according to style, according to cost, and according to fuel economy. So consider we have this let's say preference table, and we can see that, for instance, the decision maker, or the one who is actually judging those alternatives according to style, have considered that, let's say, the Civic has a score of 4 over Ascot, while i20 is, let's say, moderately more stylish than the Civic, and also for the Ascot. And the Alto is, let's say, strongly scored of 6 over Civic, 4 over i20, and 5 over Ascot, using the same actually scale of those score values that we used before. And then we calculated the reciprocals, the corresponding reciprocals that we can find in here. So we're having this 1 over 4 to this one, and also this 1 over 4 to this one. Also, we're having, let's say, those reciprocals, and also those. We just calculate them according to the scores that we have chosen. So now that we have this, let's say, preference table, or our first pairwise comparison joining this matrix, we calculate the sum. So we do the same process. We are going to normalize this this matrix. So we do calculate the sums of each columns, and then we divide the values of each cell by the sum of those columns to actually get the normalized matrix. And then after we get the normalized matrix, we do the averaging of the rows to get those final results. Okay, so this is as far as style is considered, and we do the same for the cost. We're having this pairwise comparison matrix, and we do this normalization, and after we normalize, we do the averaging of rows to get those actually priority vectors. So now we're having those actually eigenvectors calculated for the style and for the cost. And we can also do, in case of the fuel economy, since we're having some actual values about it. So we're having the corresponding miles per gallon for each of the cars, of the alternatives. So since fuel economy is quantitative, we can directly use the ratios to the sum as our priority vector. So we'd simply do the overall sum and divide each of those values over it to get our priority vector, and therefore we would have the resulting priority vector for the fuel economy, as you can see. So now we need to rank those alternatives accordingly, and as you can see that for the style, we get the priority vector for the style, and you can see that Alto has the highest rank in terms of style, and in terms of cost, we're having, let's say, the Civic as the best alternative, and for the fuel economy, we're having also the Civic as our best alternatives. Now we are having this matrix that is so we're having this hierarchy. We're having at the top, we're having the criteria weights, the corresponding criteria, and the ranks for the alternatives according to each of those criteria. So the second thing we do, we're having this matrix. This one, we need to multiply it by the weights of the criteria, this one, to get the final actually scores for each of the car. That is a comprehensive score taking into consideration all of the style, cost, and fuel economy ranks or scores. So the way we do that, again, we multiply each row by the columns. So first row by the entire column to get 0.3. So 0.13 times 0.32 plus 0.38 times 0.56 and plus 0.3 times 0.12 to get 0.3. Again, we multiply the second by the second row by the columns to get this one, and so on and so forth. And again, we are now having the ranks for each alternatives based on those three criteria accordingly to the weight of each criteria and the preference and judgment made based on these criteria to rank the corresponding alternatives. And therefore, if I want to choose a car among those three cars, I would go for the Civic that has the highest score according to the judgments that we have made in the pairwise comparisons, and according to the actual weights that we have also judged for the criteria. So based on those and on this analysis, Civic has the highest score, and therefore it is our decision after this AHP analysis process. And this is how AHP helps us actually show or present our judgment, our subjective judgment, and also to incorporate our quantitative analysis, which has done in the fuel economy criteria. We had the actual miles per gallon. So you can see that AHP has incorporated both subjective and objective judgment into the decision-making process. And based on our preferences and judgment, we can get a mathematically sound result that would help us make informed decisions accordingly.